Hey everyone, and welcome. Today we are talking about something you can't see, but you can definitely feel. We're going to pull back the curtain on the invisible force that's behind everything from a tiny spark to a massive lightning bolt. Let's dive right into the incredible world of electric charge.
You know the feeling, right? You reach for a metal doorknob, maybe on a dry winter day, and zap! You get that little shock. It happens to all of us. But have you ever stopped to think, what is actually happening in that split second? What is that spark?
Well, that little zap from the doorknob is part of a huge family of experiences. It's the very same thing that makes your sweater crackle when you pull it over your head. It's why you sometimes get a jolt from your car door. And believe it or not, on a much, much grander scale, it's the same force that creates the lightning that tears across the sky.
The culprit behind all of these things, from the tiny to the terrifying, is a fundamental property of matter. It's called electric charge. And if you can get your head around this one concept, you've basically got the key to understanding all of electricity. So let's peel back the layers.
Now, our journey to figure this all out doesn't start in some high-tech modern lab. Nope, we have to go way back, way back to ancient Greece. This is a mystery that took literally thousands of years to solve, and it all started with a really strange observation.
So, around 600 BC, the ancient Greeks noticed that if you took a piece of amber and rubbed it with wool, it would suddenly be able to pick up light things, like feathers or bits of straw. For the next 2,000 years, this was basically just a cool party trick. But then, in the 1700s, scientists started getting serious, discovering there were actually two different kinds of this effect, and then along came Benjamin Franklin, who had the brilliant insight to simplify it all, and he gave the two types the names we still use to this very day: positive and negative.
And get this, that very first observation was so important that the Greek word for amber, which is electron, ended up giving us the name for this whole field of study, electricity. How cool is that? The clue was right there in the name the entire time. Okay, so Franklin gave the charges names, but what was really important was what all those experiments revealed: a simple, totally unbreakable rule that explains how every single charge in the universe interacts with every other charge.
So here are the two players in our story. By convention, meaning they just decided to call it this, the charge that appeared on a glass rod after being rubbed with silk was called positive, and the charge that showed up on something like a plastic rod or on the silk itself was called negative.
And the rule they follow? It's beautiful in its simplicity. Any two charges that are the same, so a positive and a positive or a negative and a negative, will always push each other away. They repel. And any two charges that are different, a positive and a negative, will always pull towards each other. They attract. That's it. Likes repel, opposites attract. That one idea is the bedrock of everything we're about to talk about.
Okay, but that brings up a much deeper question. It's one thing to say a glass rod has a positive charge, but what is that really? It's not some kind of magical invisible juice. The real answer lies deep down inside the atoms that make up that rod.
Right, so here is the absolute key. Things become charged when they either gain or lose these tiny negatively charged particles called electrons. So when you rub that glass rod with silk, what's actually happening is that some electrons are literally jumping from the atoms in the glass over to the atoms in the silk. The glass rod, because it lost those negative particles, is now left with an overall positive charge. And the silk, which now has extra electrons, has an overall negative charge. See? No charge was created out of thin air. It was just moved around.
So now that we know what charge actually is, a surplus or a deficit of electrons, we can talk about its three fundamental properties. And these aren't just suggestions, these are absolute non-negotiable laws of the universe. Charge always behaves this way.
Okay, so first, charges are additive. You just add them up like positive and negative numbers on a number line. Simple. Second, charge is conserved. You can't create it or destroy it. The total amount of charge in a closed system is always the same. And third, and this is the one that's a little weird, charge is quantized.
What on earth does quantize mean? It just means that charge isn't some smooth, continuous fluid that you can have any amount of. It only comes in tiny, discrete, identical little packets. Think of it like money. You can have $1, $2, or $5, but you can never ever have $1.50. Charge is just like that. Every single bit of charge you will ever find in the universe is a whole number multiple of one fundamental unit, which we call E.
And just how small is that fundamental packet of charge? There it is, 1.6 times 10 to the power of negative 19 coulombs. The Coulomb, or C, is our standard unit for charge. That number is just ridiculously
mind-bogglingly small. And that's why in our big, everyday world, charge seems like it's smooth and continuous, but really, at the most basic level, it's all built from these tiny, identical steps.
So we know that charges push and pull on each other. We know likes repel and opposites attract. But how much? Can we actually predict how strong that force is? Well, yes, we can, thanks to a brilliant French physicist who was the first person to actually measure this invisible force.
This is the man himself, Charles-Augustin de Coulomb. Back in the 1780s, he built this incredibly sensitive device that could measure the teeny-tiny forces between charged objects. And what he discovered gave us one of the most powerful and important laws in all of physics.
And this is his law. Put simply, it just means that the more charge you have, the stronger the force is. Makes sense. But the really crucial part is that as you pull the charges apart, the force between them gets weaker really, really fast. It follows what's called an inverse square law. So if you double the distance between them, the force drops all the way down to just 1/4 of what it was before.
So how does this electric force stack up against that other fundamental force we all know and love, gravity? Well, gravity acts on mass, while the electric force acts on charge. And while gravity only ever pulls things together, the electric force can both push and pull. But the biggest difference, the one that's really hard to wrap your head around, is their strength.
So just how much stronger is it? Look, the electric force isn't just a little bit stronger than gravity. It is unimaginably stronger. That number on the screen, that's a 1 with 39 zeros after it. That's roughly how many times stronger the electric force is than gravity between a single proton and electron. I mean, that number is so big, it's practically meaningless. On the scale of atoms, gravity doesn't even stand a chance.
Which brings us to one last really big question. If this electric force is so ridiculously, colossally powerful, why don't we feel it all the time? Why isn't the entire world just a chaotic mess of things constantly flying apart or slamming into each other? The answer, of course, is that most of the stuff around us is perfectly, beautifully balanced, with exactly as many positive charges as there are negative ones. They cancel each other out, leaving our world, for the most part, electrically neutral. It's like a quiet giant, always there, just waiting for a tiny imbalance to reveal its incredible power.